everyone, myself Shivangi Desai, your instructor for the video series of data mining and business intelligence. Today's our topic is types of outliers. So let's get started. In general, outliers can be classified into three categories, namely global outliers, contextual or conditional outliers, and collective outliers. So let's start with global outliers. In a given data set, a data object is a global outlier if it deviates significantly from the rest of the data set. So we can say global outliers are sometimes called point anomalies and are the simplest type of outliers. Most outlier detection methods are aimed at finding global outliers. Consider the points in given figure. The points in region R significantly deviate from the rest of the dataset and hence are example of global outliers. To detect global outliers, a critical issue is to find an appropriate measurement of deviation with respect to the application in question. Global outlier detection is important in many applications. Consider intrusion detection in computer networks. For example, if the communication behavior of a computer is very different from the normal patterns, that is, a large number of packages is broadcast in a short time, this behavior may be considered as a global outlier and the corresponding computer is a suspected victim of hacking. As another example, in trading transaction auditing systems, transactions that do not follow the regulations are considered as global outliers and should be held for further examination. Now let's discuss contextual outliers. The temperature today is 28 Celsius. Is it exceptional? That is an outlier. It depends, for example, on the time and location. If it is in winter, then yes, it is an outlier. If it is in summer, then it is normal. Unlike global outlier detection, in this case, whether or not today's temperature value is an outlier depend on the context, that is the date, the location and possibly some other factors. In a given data set, a data object is a contextual outlier if it deviates significantly with respect to a specific context of the object. Contextual outliers are also known as conditional outliers because they are conditional on the selected context. Therefore, in contextual outlier detection, the context has to be specified as part of the problem definition. Generally, in contextual outlier detection, the attributes of the data objects in question are divided into two groups. First, contextual attribute. The contextual attributes of a data object defines the object's context. In the temperature example, the contextual attribute may be date and location. Second is behavioral attribute. This defines the object's characteristics and are used to evaluate whether the object is an outlier in the context to which it belongs. In the temperature example, the behavioral attribute may be the temperature, humidity and pressure. Unlike global outlier detection, in contextual outlier detection, whether a data object is an outlier depends on not only the behavioral attribute but also the contextual attributes. A configuration on behavioral attribute values may be considered an outlier in one context, that is 28 Celsius in an outlier for a winter, but not an outlier in another context, that is 28 Celsius is not an outlier for a summer. Contextual outliers are a generalization of local outliers, a notion introduced in density-based outlier analysis approaches. An object in a dataset is a local outlier if its density significantly deviates from the local areas in which it occurs. Global outlier detection can be regarded as a special case of contextual outlier detection where the set of contextual attribute is empty. In other words, global outlier detection uses the whole dataset as the context. Contextual outlier analysis provides flexibility to users in that one can examine outliers in different contexts, which can be highly desirable in many applications. In credit card fraud detection, in addition to global outliers, an analyst may consider outliers in different contexts. Consider customers who use more than 90% of their credit limit. If one such customer is viewed as belonging to a group of customers with low credit limits, then such behavior may not be considered an outlier. However, similar behavior of customers from a high income group may be considered outliers if their balance often exceeds their credit limit. Such outliers may lead to business opportunities. Raising credit limits for such customers can bring in new revenue. The quality of contextual outlier detection in an application depends on the meaningfulness of the contextual attributes, in addition to the measurement of the deviation of an object to the majority in the space of behavioral attributes. More often than not, the contextual attributes should be determined by domain experts, which can be regarded as part of the input background knowledge. In many applications, neither obtaining sufficient information to determine contextual attributes nor collecting high quality contextual attributes data is easy. Now, how can we formulate meaningful context in contextual outlier detection? A straightforward method simply uses group base of the contextual attributes as context. However, this may not be effective because many group base may have insufficient data or noise. A more general method uses the proximity of data objects in the space of contextual attributes. Now let's discuss collective outliers. Suppose you are a supply chain manager of an electronics store. You handle thousands of orders and shipments every day. If the shipment of an order is delayed, it may not be considered an outlier because statistically delays occur from time to time. However, you have to pay attention if 100 orders are delayed on a single day. Those 100 orders as a whole form an outlier, although each of them may not be regarded as an outlier if considered individually. You may have to take a close look at those orders collectively to understand the shipment problem. Given a data set, a subset of data objects forms a collective outlier if the object as a whole deviates significantly from the entire data set. Importantly, the individual data objects may not be outliers. In given figure, the blue objects as a whole form a collective outlier because the density of those objects is much higher than the rest in the data set. However, every blue object individually is not an outlier with respect to the whole data set. Collective outlier detection has many important applications. For example, in intrusion detection, a denial of service packages from one computer to another is considered normal and not an outlier at all. However, if several computers keep sending denial of service packages to each other, they as a whole should be considered as a collective outlier. The computer involved may be suspected of being compromised by an attack. As another example, a stock transaction between two parties is considered normal. However, a large set of transactions of the same stock among a small party in a short period are collectively known as collective outliers because they may be evidence of some people manipulating the market. Unlike global or contextual outlier detection, in collective outlier detection, we have to consider not only the behavior of individual objects but also that of groups of objects. Therefore, to detect collective outliers, we need background knowledge of the relationship among data objects such as distance or similarity measurements between objects. In summary, a dataset can have multiple types of outliers. Moreover, an object may belong to more than one type of outlier. In business, different outliers may be used in various applications or for different purposes. Global outlier detection is the simplest, whereas context outlier detection requires background information to determine contextual attributes and context, whereas collective outlier detection requires background information to model the relationship among objects to find groups of outliers. Now let's discuss the challenges of outlier detection. Outlier detection is useful in many applications, yet it faces many challenges such as the given. So let's start with modeling normal objects and outliers effectively. Outlier detection quality highly depends on the modeling of normal, or we can say non-outlier objects and outliers. Often, building a comprehensive model for data normality is very challenging, if not impossible. This is partly because it is hard to enumerate all possible normal behaviors in an application. The border between data normality and abnormality is often not clear-cut. Instead, there can be a wide range of gray area. Consequently, while some outlier detection methods assign to each object in the input data set a label of either normal or outlier, whereas other methods assign to each object a score measuring like the outlierness of the object. Now let's discuss application-specific outlier detection. Technically, choosing the similarity, or we can say distance measure, and the relationship model to describe data objects is critical in outlier detection. Unfortunately, such choices are often application dependent. Different applications may have very different requirements. For example, in clinic data analysis, a small deviation may be important enough to justify an outlier. In contrast, in marketing analysis, objects are often subject to larger fluctuations, and consequently, a substantially larger deviation is needed to justify an outlier. Outlier detection's high dependency on the application type makes it impossible to develop a universally applicable outlier detection method. Instead, individual outlier detection methods that are dedicated to specific applications must be developed. Now let's discuss handling noise in outlier detection. As mentioned earlier, outliers are different from noise. It is also well known that the quality of real data sets tends to be poor. Noise often unavoidably exists in data collected in many applications. Noise may be present as deviations in attribute values or even as missing values. Low data quality and the presence of noise bring a huge challenge to outlier detection. They can distort the data, blurring the distinction between normal objects and outliers. Moreover, noise and missing data may hide outliers and reduces the effectiveness of outlier detection. An outlier may appear disguised as a noise point, and an outlier detection methods may mistakenly identify a noise point as an outlier. Last is understandability. In some application scenarios, a user may want to not only detect outliers but also understand why the detected objects are outliers. To meet the understandability requirement, an outlier detection method has to provide some justification of the detection. For example, a statistical method can be used to justify the degree to which an object may be an outlier based on the likelihood that the object was generated by the same mechanism that generated the majority of the data. The smaller the likelihood, the more unlikely the object was generated by the same mechanism, and the more likely the object is an outlier. So today we discussed different types of outliers as well as the challenges of outlier detection. That's it for this lecture. Thank you.